Okay, let's review what an equation is. An equation is when you set two expressions equal to each other. An example of that could be if we put x plus 2 and we set it equal to 4. Another one could be 3 minus 1 equals 2. This would be considered an algebraic equation because there's a variable in it. This would just be a numerical equation, which you're used to doing. A solution makes an equation true. Sometimes we have to solve equations to find their solutions. So I'd like you to write down these three equations. N minus 1.6 equals 7.2. Four equals 2/3 x. And r over 3 equals 9. Okay, now each of these equations we have a variable and something has happened to it. We're trying to go back and figure out what it was. What makes this equation true? So here we had n and 1.6 was minus from it. So to undo that, we use our inverse operations. So the inverse or opposite of minusing would be adding. If I add back 1.6, then that's going to undo this and get n by itself. So what was n before we minused? Well, we have to add the 1.6 back. That means we have to add 1.6 back to the number on the other side of the equation as well. It's an equation, so it has to stay balanced. So when I add 1.6 back from minusing 1.6, it's like it never happened. It cancels it out. So what was n before they took away 1.6? So we add these together. 2 plus 6 is 8. Don't forget your decimal point. 7 plus 1 is 8. So we get n equals 8.8. Now, how do we make sure it's a solution? We plug it back in the original equation. So we're saying n is 8.8. Let's make sure it works. So where n is, I'm plugging in 8.8. So 8.8 minus 1.6 should equal 7.2. Okay, this is not in its most useful form, so I'm going to do it over here by lining up the decimals. So we're going to prove that 8.8 is our solution. So if I'm minusing 1.6 from 8.8, 8 minus 6 is 2. 8 minus 1 is 7. So this side became 7.2. Does that match the other side? Yes, it does. So that tells us that 8.8 is in fact a solution. Okay, I picked this example because a lot of you make very common mistakes with this. So x is our variable. It's been multiplied by 2/3 to get 4. Since it's been multiplied, I do the inverse operation, which would be division. So I want you underneath it to write divide by 2/3. If I times something by 2/3 and I want to undo that, I divide by 2/3. If I do it to one side, I have to do it to the other side. This is going to cancel out and leave me with just x on this side. So what was x before it got multiplied by 2/3? We're going to have to do a little math here with 4 divided by 2/3. So this is just a division. So since it's fraction division, remember, keep the first, flip the second. So I'm going to keep 4. So it's still 4. I'm just going to write 4 over 1. Keep the first, flip the second. So that's where I'm getting 3 over 2. Change the sign. So I just took my division problem and rewrote it after flipping the fraction. Alright, going to cross cancel where I can. 4 and 2 both share a common factor of 2, so let's reduce. 2 goes into 2 one time. 2 goes into 4 2 times. So if I multiply across the top, I get 2 times 3, which is 6, over 1 times 1, which is 1. So we're saying x is equal to 6. If x equals 6, that sounds good, but we have to prove it and make sure it works. So this is where we take our original equation, and we're going to plug 6 in where x is. So rewrite the original equation. 4 equals 2/3 times, except for we're replacing x with 6. Okay, prove that it works. Is x really 6? Okay, and we're multiplying fractions here. Cross cancel where we can. 3 and 6 share a common factor of 3. So that would give me 1 here. 3 goes into 6 2 times. 2 times 2 is 4, and 4 over 1 times 1. 4 matches 4. That tells me that 6 is the solution. Okay, this last one, we have r. What's happening to it? This line here, yes, it might look like a fraction. It is. It also means divide. So this is r has been divided by 3 to get 9. And a lot of people instantly want to say, oh, it's 3. Well, no. If I put 3 in here, 3 divided by 3 is not 9. What number was divided by 3 to get 9? How do I undo division? I'm going to times. So if I times by 3 and I times by 3 to this side, okay, if these are fractions, these will cross cancel and give me 1, which would leave me with 1r. So it's going to cancel each other out and give me r on this side. 9 times 3 is 27. Well, let's check our answer, plug it back in. 27 divided by 3 gives me 9. Is that a true statement? 27 divided by 3 is 9. Yes. Sometimes they are easy enough to check in your head. Other times they're not. These other two were not. This one, you could have checked in your head. Alright, so those are equations and solving simple one-step equations. Now let's talk about inequalities. Inequalities. Okay, inequalities compare two quantities. Quantities using these symbols. These symbols should be familiar to you. This would be greater than, less than. With the line under it means greater than or equal, so it can be equal and it can be bigger. Less than or equal. So with these kinds of things, we're going to talk about a couple real life examples where you might use these. So let's say Annie must score. Let's write down these situations so we know where we would use these in real life. Annie must get no less than 85% on her test. I want to put that online test. If you can, I know you can't see that very well. It's just test. Okay, Annie must get no less than 85% on her test. So we're going to have a variable for the thing that might be different numbers, and in this case it would be Annie's test score. So I'm just going to write T represents test score. So I know what T represents, defined my variable. Now we're going to be comparing her test score to 85%. Now we need to determine which of these symbols would go in here to fit this statement. She must get no less than 85. So, no less, could she get equal? Yes. It would be alright if she got equal to 85. So, I know it's going to have a line under it. Equal to 85 works. Now, since it's no less, equal is not less. Bigger is also not less. Make sure you're writing all of this in your journal. So the mouth needs to be open towards the T because we want her test score to be larger than 85. If I put the mouth open towards the 85, I would say 85 is the highest she wants, which would not be true, would it? Okay, let's try another one. Tim must get less than 3 strikes. And not be out. I'm not going to write that in there, but Tim must get less than 3 strikes. Alright, the thing that could be different numbers would be the amount of strikes he can have. So I'm going to use S for strikes. So I'm defining my variable. S represents the number of strikes. Make sure your head is up and you're writing everything I do. Okay, so we're comparing the number of strikes to 3. Now, thinking about this, can it be equal? Can he get 3 strikes and still be out? No, so this is not going to be an equal. It's going to be one of these two. So which way do I want the mouth facing? The number of strikes to be bigger than 3? Or the number of strikes to be, well, less than 3. Since 3 is the biggest, I want 3 to be bigger than what he gets. I'm going to put the mouth open towards 3. S has to be smaller than 3. Now the thing about inequalities is inequalities can have many, many solutions. So instead of writing down every number that could possibly work to make it true, we use a graph to show it. So we're going to graph the solutions to some inequalities. So let's say you have the inequality. I want you to skip one line for a second. We'll come back. So skip one line. I want you to write R is less than or equal to -2. Now there are 2 kinds of dots we use when we are graphing inequalities. If you are doing either of these signs, greater than or less than, we don't include the number that we put the dot on. So these are going to have an open dot. Greater than or equal to or less than or equal to, on the other hand, we are including the number. It can be equal. So this would be a filled dot. So looking at the example we wrote about R. R is less than or equal to -2. We're going to draw a number line. And we're going to find -2 on there. So if I put 0, -1, -2, -3, 1, 2, that's good enough. Okay, this can be equal to -2, so I want to include -2. So I'm going to put a filled dot on -2. So a lot of you mess up because you forget the filled dot or open dot. Remember, if it's included, I want to keep you, I'm going to fill you in on it. If not, I want everything really close to it, but not that number exactly. Now we got to determine which way the arrow goes. R is less than -2. So if I put in a number, let's say I put in -1. Is -1 less than or equal to -2? No, this side does not work. Less than or equal to -2, I've got to go the direction that's less than -2. So everything from -2 on down the number line is a solution. Okay, let's try one more example. 1.6. I'm not going to say it just so that I want you to think. Compared to M. Make a number line. Since it's 1.6, I'm just going to go between 0 and 1. And then 0.6, that's in tenths. So if I split this into 10 pieces, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pieces. 1.5 would be right here. I need to be able to find this number on the number line. That's all that really, really matters. So if 1.5 is right here, this would be 1.6. 1 6/10. Oh! I have done something wrong. Let's fix this. This would have to be 1 if I'm going to go to 1.5. This would have to be 2. If not, it'd be at 0.5. I'm sorry. Need to fix that. Okay, I'm in the positives. Sorry, I'm between 1 and 2. So 1.6 would be 1/10 more than 1.5. Because this is not included, I'm going to put an open dot on 1.6. It can't be equal to 1.6. Now, M, look at the way the mouth is facing. The mouth is open towards the M. That means M has to be larger than 1.6. So which direction is larger than 1.6? To the right. So draw an arrow. Every number this direction is a solution to this inequality. Give you just a second to make sure all that's written down properly. And then I'm going to flip to the next page. All right. If you still have space, keep writing. Some of you write big like me though, so you're going to have to write on the next page. All right. Independent variable. Independent variable controls the situation. Another word for it is input. The dependent variable this one changes. I'm going to put in all caps because of the independent variable. Okay, this is also known as the output. Couple simple examples of where you might have this. The more you study for a test, the higher your score will be. The part you have control over that controls the situation is how long you study. Because you studied, your test score should go up. So, independent in that situation would be the time you spent studying. The dependent would be your test score. Another example, the longer I leave the water running, the more water I waste. The part that controls the situation is the fact that I left the water running, so it would be the time that the water's running. The dependent is how much water gets wasted because I left it on. Okay, cause and effect is kind of a way to think of that one as well. Alright, in these kinds of situations, there are 4 different ways we can look at them. We got context. Context is just the words. Okay, we can make a table. We can make a graph. And we can write an equation. So we're going to do an example where we do all 4 of these. So I want you to find about the halfway mark of your math journal here, and we're going to try and fit it as best as we can in these 4 squares. Okay, so context. This is just going to be our wording. So in this situation, a museum charges $3 admission. Admission means to get in. Make sure you're writing everything I do. Don't be messing around. Charges $3 admission and $2 for each additional tour. Okay, we have a situation. So we got $3 to get in and then $2 for each additional tour that you have to do with a guide. So we're going to make a table of this information. We have to define what our input is and what our output is, though. Input is what controls it. Output is what changes because of the other one. So the part that we have control over, we're already going to the museum. The part we have control over is how many tours we choose to take. So tours, we're going to give this one the variable of x. Okay, so input is tours. That's the part we have control over. The part that changes is the cost. We're going to give that the variable of y. So I can choose to do 0 tours. That's where my cost starts. But no matter what, I'm going to this museum. It's going to still cost me a total of $3 to get in to the museum. From there I could go 1 tour. 1 tour would be $2 plus the $3 to get in. My total cost is going to be $5. 2 tours would cost me 2 times 2, which would be $4 plus the $3 to get in, so that'd be $7. You don't have to just go in order 1, 2, 3, 4. If we skipped and said, well, what if I did 4 tours? 4 times 2 would be 8, plus $3 to get in would be $11 total. Sometimes you might be given something like this where you have 15. So it cost you $15. How many tours did we decide we'd go on? We forgot. So let's think backwards. It cost $3 to get in. That leaves me $12 spent on tours. If I spent $12 on tours, that means we did 6 tours. Okay, so we have it in its context. We have it in a table. let's make a graph. You're going to have to write kind of small. So in 3 lines, I'm just going to make a little L. My x-axis, my y-axis. This one, x represented tours, so I'm going to label it tours. My y-axis represented cost. Okay, looking at the numbers I'm going to graph, we can get this just from our table. So I'm comparing tours to costs. So I went 0, 1, 2, 4, 6. So I'm going to number this by ones. 1, 2, 3, 4, 5, 6. I know I'm writing small. So 0, 0 here's in the corner. My cost goes up to about 15, so I'm going to number by 2's on this other side. So 2, 4, 6, 8. And as long as you're consistently numbering, the axes can be different numbers, but you have to make sure you don't skip. I can't go 1, 2, and then make this one 6. It's got to be 1, 2, 3. This is consistently numbered by 1's. This is consistently numbered by 2's. Now we're going to plot our points. So we have 0, 3. So 0 tours still cost $3. So I'm going to put a dot right there on the y-axis between 2 and 4. 1 tour cost $5. One tour, the total cost was $5. So 1 tour, I'm going to put a mark at 5. 1, 5. I'm getting all of my ordered pairs from my table. 2 tours cost $7. 3 tours, we didn't have a number for that. We could find one, but we're just going to graph what we have on here. So 4 tours is 11. And 6 tours was 15. As you can see, if your graph is fairly even, it makes a nice straight line. This is called a linear relationship. It's constantly growing by the same rate. No matter what, it's going to be $2 more every single time I add a tour. My starting point was at 3. So here, in this box, I want you to write equation, and I'm going to remind you of a way to help you write any equation. I want you to write output equals start plus, or put a minus up there because you could be minusing. If it's going down, it's minusing, right? Okay, so the starting point, remember how we always start somewhere? And then it's either going to go up or down. That's why the plus or minus. The rate times input. I'm just going to write in because I can't quite fit it. So you'll see that from this example. So our output was cost. So we're going to write y equals. Now our starting cost. Where did our cost start? At $3. So my starting point here was 3. No matter what, we had to pay $3 to get in the museum. Now, my cost went up or down. This is where you select. Am I going to do minusing or adding? In this case, adding, because my cost went up. How much did it go up by every single time? That's my rate. My cost went up by $2 every time because it costs $2 for each additional tour, right? So I'm going to write $2 times the number of tours, which was X. And I don't have to write that dot in there. It could just be 2X. But there's my equation. My starting point and my rate. Okay, we're almost done. I'll give you another minute just to copy that down. Sometimes you will be required to write an equation from a table or from a graph. Sometimes you'll be asked to graph from a table or from an equation. We're going to practice both of those. Okay, now I'm moving on. So we're going to practice graphing from an equation. You need to write small so that you can fit it all on this page. We're just going to do a very basic one, and we're just going to do one. So I want you to write the equation y equals 2x minus 1. Okay, if you're given this equation and they ask you to make a graph, I want you to make a basic graph, and you have all 4 quadrants because we don't know where this one might go. It could be positive or negative. Make some tick marks representing ones. When you have an equation like this, it's saying our output can be found, our rate is 2, and our starting point's at -1. But you can easily figure that out if you just make an XY table. This is where you get to pick the X's, but whatever you pick for X, there's going to be a Y output. So I'm going to always like to pick 0 for X to begin with. So I want you to plug in Y equals, so we're going to do 2 times 0 minus 1. 2 times 0 is 0. And then 0 minus 1, I'm going to end up at -1. That's my starting point. Okay, I'm going to go to +1. So 2 times +1 minus 1. 2 times 1 is 2. And 2 minus 1 is 1. If I plug in 2 times 2 minus 1. 2 times 2 is 4. 4 subtract 1 gives me 3. If I put in 3 here, I could pick other numbers as well, but 0, 1, 2, 3 will work just fine. So 2 times 3 minus 1. 2 times 3 is 6. 6 minus 1 is 5. Okay, I have 4 different points that I can plot on my graph. So let's now find these. These are just ordered pairs. So 0, -1. I go to 0 on the x-axis, -1 on the y. I'm going to put a dot right there. 1, 1. So I'm going to go to +1, +1. So +1 on the x, +1 on the y. Put a dot right there. +2, +3, so I go to +2 on the x, up 3 on the y, +3, +5, so I'm going to go over to 3 and up 1, 2, 3, 4, 5. And as you can see, especially if you had perfect graph paper, this makes a nice straight line. So that's graphing from an equation. We made a table, so if somebody gave you a table, you could easily graph from a table as well, right? Okay, last little part we need to talk about is writing equations from graphs or from tables. So write equations. That's what we're doing here. If you can figure out the starting point and the rate, it's easy to do. We're almost done with our notes. So if I want to write an equation, let's say I have this table. I'm just going to make an XY table. We're going to do 2 tables and then a graph, so write kind of small if you can. So here's going to be the second one. We'll write the equation underneath it. And it's not always x, y. It might be a, b, or whatever they give you. Just put the right variable in the right spot. Okay, and then a small graph over here. All right, this first table. 0, 6, 1, 5, 2, 4, 3, 3. The second table. 1, 4, 2, 7, 3, 10. Okay, on this graph, you're going to number by ones. Okay, so I numbered to 7 on each one of these. And you're going to put a dot at 0, 0. A dot at 1, 2. A dot at 2, 4. And a dot at 3, 6. So we got all the clues we need to write an equation with these numbers. We just have to look carefully and analyze the relationship. Give everybody 1 minute to get those drawn so that my explanations make sense. Okay, I think everybody's done. So let's look at the relationship here. As this goes up 1, this goes down. As this goes up 1, this goes down 1. So on the side here, I want you to write +1. But what's happening here is we're minusing 1. What's going on here? We're adding 1. What's going on here? We minus 1 again. So you can see that pattern going on here. That's your rate. As this goes up 1, this goes down 1. This tells me I'm minusing. So I'm minusing here. But I'm minusing from something. If I've got 0, I get 6. If I've got 1, I get 5. If I've got 2, I've got 4. So my output can be found. You always can start that way. Let's do that for all of these. My output equals. My output equals. In this case, they're all Y's, but sometimes they might be different letters. Now I want to figure out a starting point. Where does each one of these start? Starting point is where x is 0, so this one's kind of a give me. When x is 0, my starting point is at 6. So 6 minus, why do I know it's minus? Because this is going down. So this is where I need to think a little bit. If I'm taking 6, what am I minusing to get 0? Well, sorry, what am I doing to 0 to get this? Well, I'm minusing x. If I take 6 and I minus 0 from it, I get 6. If I take 6 and I minus 1 from it, I get 5. If I take 6 and I minus 2 from it, I get 4. 3, I take 6 minus 3, I get 3. I know it was minusing because each one of these is going down. Okay, let's look at this one. As this goes up, 1, 4 to 7, that went up 3. So this is growing. This is a growing pattern. So I'm going to be adding. This one went up 1, This one went up 3. So my rate is growing by 3 times as fast as the x is growing. So y is growing 3 times as fast as x. Now I just need to figure out where I'm starting. If I'm taking and timesing x by 3, so if I do 3 times 1, 3 times 1 is 3. What do I need to do to it to make it turn into 4? 2 times 3 is 6. What do I need to do to 6 to make it into 7? Okay. 3 times 3 is 9. What do I need to do to make it 10? That's where your starting point is. What am I starting at? I'm starting at 1. Because I have to add 1 to each of these to make it become this number. So 1 plus our rate, which was 3, times our input. Okay, when you have a graph, I'm going to tell you right now the easiest thing to do is to make a table. So over here, let's make a table of our values. We've got x and y. We have 0, 0, 1, 2, 2, 4, and then 3, 6. Sometimes you can just see what's happening. If I look at x, what can I do to x to make it turn into y? We can still look at a rate. As this goes up 1, 0 to 2 goes up 2. As I go up 1 here, this goes up 2. So we're seeing this side grow 2 times as fast as x. Do I have to do anything besides multiplying by 2? Let's check. 0 times 2 is 0. 1 times 2 is 2. 2 times 2 is 4. So the only thing that happened here is take and times x by 2. Our starting point is 0. And I could write plus 0 on there if I wanted to, but I don't have to. Starting point is at 0, and it's growing by 2 every time.